everyone. Today we're going to start chapter 14.5, and we've hinted on how temperature affects reaction rates, but this section goes into a little bit more detail about it. This section is very concept heavy, so make sure that you guys ask questions if you run into any. As an introduction, it says the rates of most chemical reactions increase as temperature rises. This is considered a direct relationship. We can actually use everyday examples to see this happen. For example, if you're trying to make dough for bread, typically it's going to rise faster at room temperature than if you were to put it in a refrigerator. Also, plants. Plants tend to grow faster or more rapidly in warm weather than when it is cold outside. And another example is the glow sticks or light sticks that you have to snap. These tend to glow brighter at a higher temperature. All this has to do with temperature and reaction rates. How are temperature and rates affected then? So how is temperature effect reflected within the rate law that we learned earlier in the chapter? Well, one thing to note is that you're going to tend to have a faster rate at a higher temperature, and this is typically due to your rate constant tends to increase with temperature. We talked about rate constant, which is K, and how it's influenced by temperature and not necessarily concentrations. So rate constant plays a big role. Now, even though I say rate constants aren't really affected by concentration, reaction rates still are. Reaction rates, we still have to take into consideration the reactant concentrations and temperature. And we have this be taken into effect and put together through something called the collision model. This collision model is actually based on the kinetic molecular theory that we talked about in the gas chapter, and it accounts for a lot of things that we see within the molecular level. One of the central ideas of the collision model, though, is that in order for molecules to react, they have to collide, hence the name. So, with this central idea, there are three things that we need to talk about. One, the greater the number of collisions, the greater the reaction rate. And this is because the more collisions you have, the more possibility you have of a reaction occurring. Two, as the reactant concentration increases, the number of collisions is going to increase, and therefore my reaction rate is going to increase. And this makes sense. If you add more things to a container or to a reaction, there's more possibility of things colliding. It's like if you put more people in a room, you're going to collide with them more. And then the third thing, increasing temperature actually increases speed. We learned this in the kinetic molecular theory. And if molecules are moving faster, when they collide, they actually collide with a lot more energy. And therefore, reaction rates are going to increase as well. Another thing, and actually probably a lot more important than a lot of things that we've been talking about, is this idea of an orientation factor. For most reactions, molecules actually have to be oriented in a certain way for a reaction to even occur. So, the relative orientation of molecules during collision is going to actually determine whether those atoms are positioned in a way in which new bonds can actually form. So, what do I mean by this? Well, here I have two things and they're colliding. On this one, we're going to say that the green is chlorine, and chlorine, this one's oxygen, and this typically is nitrogen for blue. If they collide where chlorine hits the chlorine on this molecule, chlorine gas tends to form, and that's what we want to happen. This is an effective reaction. However, if the orientation is slightly off where chlorine is going to hit oxygen, this is an ineffective collision. No chlorine gas is actually made. So again, orientation plays a big role. Another thing that plays a big role in terms of temperature and this collision theory and reaction rates is this idea of something called an activation energy. So, activation energy is basically going to be how much energy does a reaction possess in order to occur. And typically, this energy is going to come from the kinetic energies of all of these molecules colliding. So remember, Kinetic energy is the energy of motion. Energy of motion. This energy actually helps stretch, bend, break bonds, which ultimately leads to chemical reactions taking place. And the minimum energy required to actually have a chemical reaction take place is called an activation energy. And this value is going to vary from one reaction to another. And so, a good example of this is if you're a golfer and you are trying to hit a golf ball up a hill, you have to hit it with enough energy for it to get over that barrier. And if it doesn't have enough energy to get over the barrier, the ball doesn't go up the hill and into the hole that we want it to. Same thing happens with reactions. If it doesn't have enough energy to make it over the barrier, the reaction's not going to happen. So here is the image that we use. Again, oftentimes reactions have this same barrier that they have to get over as well. So to visualize energy changes throughout a process, a reaction coordinate diagram, like the one we have over here to the right, typically illustrates what's happening or this little barrier that we have to get over. So the diagram actually shows one thing that we've already talked about in terms of thermodynamics, and that is the change in energy. So remember, the change of energy is your final energy minus your initial energy. So the energy of the final products minus the energy of your initial products. However, there are a couple other things on this diagram that you haven't quite learned. One is the top of this high point, this top. This is called a transition state. So how is the molecule breaking apart? So here we'll see that nitrogen bonded to carbon breaks off at our transition state. And these two things up here are called activated complexes, or the species present at that transition state. Then, as soon as it makes it over that barrier, you're going to see that it reforms into the correct molecule it should be in. Now, this energy gap from the top of this hump all the way to where our reactant started, so let's label this reactants so you guys know, and products, from here to here, this is labeled EA, which is called our activation energy barrier. So what does that mean in terms of temperature? Because this whole section is about temperature. Well, at a higher temperature, since these molecules are moving at a faster speed, they have more energy. That means more molecules tend to have enough energy to overcome this barrier. So in simple terms, higher temperature, faster speed, more energy collisions. And so the reaction is going to tend to happen. Now, I said there's a little bit of math, and we're going to actually go over this more in detail tomorrow, but the fraction of molecules that have energy equal or greater to our activation energy is actually given the expression F equals E. Remember, that's the exponential button on your calculator. To the negative, activation energy divided by R, which is a gas constant, times T, which is temperature. Now, to tie this into what we've been learning, especially with thermodynamics, let's talk about how does this look for an exothermic versus an endothermic reaction? Well, an exothermic reaction, again, remember this means that the reaction is going to release energy. This means that our products is going to have a lower energy than our reactants because it has given off some of that energy. And the energy change for the reaction, one thing I want you to know, has no effect on the reaction rate. So whether it's an endothermic or exothermic reaction doesn't matter for the reaction rate. The rate solely just depends on the number or the value of my EA, which remember, EA is activation energy. Generally, if I was going to put this into a statement, the lower your activation energy is, the faster the reaction, because you don't need as much energy to get it going. Endothermic, on the other hand, this means that your reaction absorbs energy. And because it absorbs energy, typically your products are going to have higher energy than your reactants because it's gained some. So if it's absorbed more, of course, you're going to add more energy to it. So typically your activation energy is equal to your change in energy plus your activation. Here are two ways you might see a reaction coordinate diagram illustrated as both endothermic versus exothermic. So notice here, endothermic, my products have higher energy than reactants, showing that it absorbed some kind of energy. So my activation energy is a lot higher. Whereas my exothermic, this shows that my products have lower energy than my reactants. That's because I've released some. So my activation energy is not quite as a big difference. To finish it out, the last few slides, this is what we're going to mostly talk about tomorrow, but I am going to introduce it today, Monday, we're going to talk about it, the Arrhenius equation. Arrhenius, you might have heard that name before. He worked with acids, but he also did a lot of other things in terms of chemistry content. He actually saw that all of these things affect whether or not a rate was going to happen, and increasing temperature was a nonlinear process, and a lot of things played a role in reaction rate with temperatures. And he found that most reaction rates had to obey an equation based on several criteria. The first, the fraction of molecules possessing energy had to be equal to the activation energy or greater. He also noticed that the number of collisions per second played a role, and the fraction of collisions that had the appropriate orientation also played a role. So all of this information was actually collected into an equation that, again, we will solve in the next class. K, which is our rate constant, equals A value is our frequency factor. So this is where they played into role the number of collisions and correct orientation. E, this is the button on calculator. That's your exponential button. To the negative, EA is activation energy. R, I said, was a gas constant, and our gas constant is 8.314. And then T, it says absolute temperature, which means that it is in kelvins. Again, we're going to work with this reaction again in the next class. But a couple things I want you to know about it in terms of concept is typically as your activation energy increases, your rate constant is going to decrease because the fraction of molecules that actually have the energy to overcome that activation energy is smaller. So if I had to put that in a sentence, reaction rates decrease as activation energy increases. That is the end of today's lesson. If you have any questions, please make sure that you guys come ask, and I hope you guys have a great day.